Hello, good day. Welcome to today's lesson. Today we begin the final unit for this course, and today we would be looking at part 1 of spatial analysis. So, as we often do when we begin looking at any new topic, we start with some definitions, and at this point I would like to take the opportunity to remind you, please make every effort to ensure that a lot of these new terms and definitions and concepts that you encounter for the first time, that you understand what they mean, that you have some idea of the definition, so that when you write you can use the terms appropriately. Because when you use the terms out of context, you're not helping yourself, especially in exam settings. Okay, so now that I've reminded you and I know that you've taken heed of what I've said, let's continue. Right, so what is spatial analysis? Spatial analysis encompasses a wide range of techniques that can be used for various things. We can actually perform analysis or analyzing within the ArcGIS environment, for example. We can do spatial analysis. We can compute things, generate numbers, areas of features, etc., determine distances. Spatial analysis would also allow visualization. So visualizing a map, looking at a map, whether it's on screen or on a paper map, and trying to understand what that map is telling you, that is a form of spatial analysis, as simple as it may seem. Spatial analysis may also involve simplification of data. Simplifying, for example, would be generalization into broader categories. We've talked about this in previous lessons, as well as generating theories regarding some particular phenomenon. All right, so precise definitions for each of those terms are provided on this page. I am not going to go through that with you. It is there for your benefit. Okay, so we continue. So what kinds of operations, broad operations or broad category of operations that can be carried out when we're doing spatial analysis? What I want to point out to you here is that when you perform spatial analysis, bear in mind spatial analysis can take place in one of two forms. It may be on the coordinates, or in other words the features on the map. So spatial, so that's the spatial aspect of it, right? Analysis on the map. Analysis operations can also be carried out on the attribute data. Because if you recall, as we've been talking about all semester, every GIS data layer is made up of two important components. You have the map component and the attribute table. You cannot have a GIS data layer with one component and not the other. So therefore, when you carry out spatial analysis, bear in mind you can do it either on your map or on the attribute table. And most oftentimes you find it would be dynamically linked, because if you carry out a selection query on your attribute data, you will actually see the results highlighted on your map. So what would spatial analysis output look like? We can categorize that as well. The output can be descriptive, and when we talk about description in with regards to maps and spatial data, you're basically looking at factual information. In other words, what characteristics of those features actually exist. So it can be descriptive. For example, when you look at a map that actually shows existing characteristics of features, whether it is the height of something or the size of something, those would be descriptive maps. Spatial analysis can also give explanation, so you can have explanatory maps. Again, in all cases, remember your results can be both maps or tables. So what do we mean by explanatory maps? The maps can present possible reasons for certain patterns and trends of different phenomena. For example, what conditions exist in this particular area that will encourage flooding. For example, you might be looking at elevation below a certain height. You might be looking for certain soil types. So maps showing that kind of information can actually explain why flooding occurs in an area. Maps may also be predictive, meaning they can show possible outcomes of a phenomena based on current patterns and trends. So in other words, I have historical map information based on the trends that I've observed over time. I can project that certain things will happen and the map would look in a certain way. Alright, so those are some categories of maps that can be produced from spatial analysis. Right. Okay, so we continue. So what are some of the ways that we can manipulate spatial data? So we have done some spatial queries already, according to the labs that you would have completed. Spatial queries may involve examples like intersections. What features intersect each other? For example, if you look at this graph, this schematic below here, it gives an example of what some of these queries might be. So if you have two features that intersect each other, the green represents the output, so that would be your result. So these are all of these are examples of spatial queries. Then one that you should be familiar with as well would be buffering. For example, you apply a specified buffer distance around a road or around a river. This type of operation is what we refer to as proximity analysis. Proximity because you're usually interested in what features occur within that boundary or what features occur outside of that boundary. So we're talking about proximity here. Overlay, as I said, all of these here are examples of overlay operations. We mentioned buffering. If you recall, this is an example of a buffering operation and the results generated here. And then we also have map algebra. Map algebra is more specific to the relation of raster data sets. Not sure if I have it in this lesson, but we would have addressed it before. Okay, so all the other examples we talked about would be spatial operations conducted in vector. Map algebra, please be reminded, is conducted on raster data sets. Right, so as I said, these are some examples of overlay operations with vector data. You have the intersection here. Green represents the results that would be returned. Union gives you everything from the two different data sets. Symmetrical difference, if you look at it, is the actual opposite of intersection. And difference gives you only what is returned from one data set. Alright, so these are just a few examples of some of the spatial analysis operations that can be carried out in GIS. Okay, so let us look at spatial analysis in terms of the different levels. Okay, so if you recall in one of the previous slides, I mentioned that visual analysis is an example of spatial analysis, and when you have to do any kind of spatial analysis, visual analysis is always the first one you would conduct. And what is visual analysis? Is a visual observation of the data, relationships and trends on your conventional maps or on your computer screen. So you often have to start with a visual assessment of the data. That visual assessment will give you some idea of what those relationships look like and what you would be able to do with it moving forward. The next step would be spatial operations. In other words, you often have to organize and prepare your data for you to move to the next level or to a higher level of spatial analysis. For example, you may need to carry out operations to do some buffering. You may need to clip portions out of your data, or you may need to do some overlay analysis to, for example, identify which areas intersect each other. Maybe that is the area that you're interested in. So some preparation of your data would need to be done. So this would be your step 2 with your spatial operations. The next step would be spatial analysis. What happens in spatial analysis? The process of extracting and creating new information about a set of geographic features. What do I mean by that? For example, you may perform spatial queries such as select by location the features that are contained within another layer. So you're talking about containment here. You would not have been able to run this type of spatial analysis if you did not already prepare your data in step 2. Alright, this note here is really just for your benefit here, briefly explaining the clip function and the overlay function. And the final step in spatial analysis is what we call spatial modeling. So this goes a little bit beyond selection and queries, etc. And what is this? This is an analytical procedure that we apply in GIS, and it may be of different types. For example, the first one, you may have geometric modeling. When you remember, when you see that word geometric from the word geometry, it is always associated with the feature size, shape, and location, right? So geometric modeling. An example of that would be calculating distances between features, or generating buffers around features, or calculating areas of features, right? So what we have happening here are operations that are being applied to the various features within one data layer. You also have another type of spatial modeling, which is called coincidence modeling. Coincidence modeling relating to features occurring within the same geographic location. So coincidence, they occur within the same geographic location. An example of that, polygon overlay operations, okay, such as intersect. Intersect would produce, if you recall, features within two separate layers occurring within the same geographic space. Another example of coincidence modeling would be union. If you recall, the union results give you everything from both layers, so they occur some in the same space and some next to each other. We also now have adjacency modeling. These are spatial relationships of features to each other. This may involve different layers. Alright, the coincidence modeling also involves different layers. So it may involve different layers and features of this, or features of the same layer. So this third one here, it may be different layers or the same layer. For example, you have two properties next to each other sharing one boundary. So we have adjacency. So bear in mind, the name of the type of spatial modeling clues you into what it exactly what this type of spatial modeling is. Geometric, coincidence, and adjacency. And again, just to emphasize, it is always helpful to know an example, not only for your understanding, but to demonstrate your understanding if you have to be writing essays or short answers. So we move on. So what are some of the tools that can be used for spatial analysis? This means now we're getting into the ArcGIS, 'ArcGIS, 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 'ArcGIS Alright, so we know that GIS can provide a set of tools that allows the user to perform a number of operations on both the map and the attribute data. We talked about that in an earlier slide. What are some of the common tools that we have been using? So try to think back in your mind's eye in the GIS, the ArcMap environment, having used some of these. So you did selection queries. You were able to do two types of selections. You could do select by attribute or select by location, right? So bear in mind, select by attribute, that's your analysis on your table or tabular information, or select by location, that would be analysis on your map. Additionally, you had tools available to do manual selection. There was the find tool, and then you had a number of tools available to you in the Arc toolbox. Alright, and this Arc toolbox, if you recall, that's that little red icon that we have been using, which houses a collection of spatial analysis tools. So this is where you would find some familiar tools like the clip function, buffering, overlay, etc. So we continue. So if you recall, we mentioned that one of the important functions of spatial analysis is to prepare your data. So what are some examples of preparing your data? Pre-processing operations. For example, you're going to have to remove errors from the data, that original data that you've received, whether it is that you generated it yourself or you got it from a third party. You have to edit that data for errors. Additionally, you will have to compile your map. So all preparatory work required to prepare for the map publication. So related to that, remember I mentioned previously that part of the preparatory work would also include organizing your data, maybe generalizing and organizing into broader classifications. That would be required for the particular type of analysis that you plan to do. Additionally, as part of data preparation, a common source of error that often occurs during registration of multiple data layers would have to be corrected. So this would be part of the data correction as well. For example, if you collect data from different sources, not every data layer would necessarily have the same coordinate system that you intend to use. So you may need to do some change in projections. Some data layers may not have any information recognizing the coordinate system, so you would need to add that information. So registration would need to be done. Okay, so these are some of the things that would need to be prepared before you can carry out higher levels of spatial analysis. Okay, registration may be necessary because of differences in the following. As I mentioned before, the source of the data was different. You got them from different agencies, etc. There may have been errors during the input of the data. There may also have been differences in coordinate systems, as I mentioned. Right. So if you have those kinds of problems in terms of inconsistencies in coordinate system, what is the solution? Irregularities can be reconciled in the GIS using a set of algorithms to perform a mathematical conversion of your coordinate system. Now, you don't have to be concerned about the math behind that, because ArcGIS has nicely provided some tools for you that would automatically do that for you. Examples of those tools that you would find in the Arc toolbox would be define projection. What define projection does is it identifies the projection type that has not been defined on a data layer. Or you have another tool where called projection, that would allow you to change projection type from one projection and coordinate system to another. Other examples of data preparation may be edge matching. This is performed to reconcile shape and location discrepancies between two adjoining maps, creating a seamless layer. Let's look at what that is. For example, you have two data maps that you need to put together. You have map sheet A and map sheet B. Notice you have some inconsistency along the boundaries here with the feature. So the process of actually, let's call it matching all of these together to make one seamless map, we call it edge matching. So that should be easy enough for you to remember, edge matching. Okay, so we continue. We're looking at spatial retrieval, classification, and measurement. Right. We are still all in that topic of spatial analysis. Right? So a part of spatial analysis may be data retrieval, meaning I want to retrieve a small subset of information from my GIS data layers, either on your map data or your attribute data. For example, location, based on location, so I'd be looking at the XY coordinates on the map, or I might be looking at retrieving a subset of information as defined by the type of spatial relationship they present on the map. For example, as I said, intersection. Do I have two data layers where the features intersect with each other in the same geographic location, or do I have certain features that occur within the boundaries of another? So these are examples of data retrieval where I have defined the criteria that I want. Additionally, part of preparation is reclassification. Again, I've mentioned this already, so this is reinforcement. At times you will find that you need to categorize your geographic objects based on a similar set of conditions. Okay, for example, you got some data with a lot of detail, a lot of fine details in terms of soil type. Maybe I don't need all that fine detail. Maybe I can categorize the soil types under broad categories. Okay, and this type of operation or this step is often carried out within the attribute table, and once it's completed within the attribute table, it would be reflected on the map. Here's an example of that reclassification that I was talking about. So you have your source layer, this is the original layer, and your output layer is the final output from your reclassification. So you would go into the attribute table and look at what we have here. We have different layers labeled A, B, E, and I. If you look at, so these are the list of your different polygons. Now what we've done, we've reclassified them. So now we want to call polygons A, all the polygons A and polygons B, we want to call all of them 1. We haven't really made much change to the others, but since we're using numeric assignments, the rest would be 2 and 3. This is the result. Notice A, all the A's and the B have all been assigned 1. So now we actually have what should be one large polygon. Oftentimes in GIS we could neaten this up by actually using an operation called dissolve to dissolve these lines, separating, or should I say these lines intersecting polygon 1. Okay, so this is an example of reclassification. Then we also have, when it comes to spatial analysis, we have some simple selection techniques that can be used as well. We have on-screen queries. What does that mean? These are features that would be selected by the operator manually using the cursor to gather information about specific features, and you all would have done this. For example, you would have used the identify tool that you would get from your floating toolbar. That's the one that looks like there's a little cursor, and I think it's like an eye on it, and you would use that, click on a feature, and you get information from it. Alright, so that's an example of on-screen query. Then you have a spatial query. So this is selection based on the attribute table data, where attributes are compared against a set of conditions. This is what you would have been doing when you use the select by attribute tool. Okay. So what does this selection operation look like? If you're doing a select by query, if you're doing an say for example an a spatial query using your select by attribute tool. So this operation normally identifies features that meet one or several criteria. So what do we mean by criteria or conditions? Criteria are used as a benchmark or a yardstick against which attributes or geometry are checked. Alright, so for example, here is a query that you would have performed. Select, so remember you're using your select by attribute tool. This is what the query would look like. Select from the schools layer the field name. So you're looking for a record in the field called name that is equal to San Juan Secondary School. So select from, so this is what you're doing. You're telling the system select from the data layer name schools, the field name called names, and you're looking for a record in that field name called San Juan Secondary School. Okay, so this is an example of a selection operation, and the features that would be found that satisfy the criteria are selected and may be exported for use as a new layer. So typically we didn't really do much of that in terms of exporting new layers, but certainly you would have seen it highlighted on your map as well as in the table. Then we have some other selection operations where we have set and Boolean algebra. So these would be some operators that you'd be familiar with, right? For example, you have less than, greater than, equal to, not equal to. And if you recall, you should have seen some of those operators when we were doing our query. In addition to these, we also have other operations such as or, and not. So I believe certainly in addition to these operators that we just looked at, you certainly would have seen or and on some of those tools that we have been using. Okay, what I want to point you to as well, this little box here, just a note to highlight to you is the in terms of the or and operators, the result of those would be this. For example, when you use the AND operator between two different layers, it produces the results of an intersect. When you use OR, it produces a union. So if you look over here on this chart, you could clearly see that each circle represents a data layer. So when you have A and B, the result of that is an intersection. Over here we have A or B, the result of that is a union. If you recall, a union gives you everything. Okay, I'll just point you to one more. We have A not B, it returns only A. You don't want anything returned that gives you B at all, not even the intersection. Alright, so this is how some of these operators work. Then we have our proximity and functions. Again, this should be reinforcement for you. By this time you should know exactly what buffering is, right? So proximity functions, these are predefined areas that would be applied around a geographic object, whether it's a point, a line, or a polygon, If you recall, for example, here is one buffering around a line segment, possibly a river. You can do it around roads, utility lines, etc. And this function we call buffering. If you recall, the buffering should be found in the ARC toolbox. So examining areas it is used to examine areas surrounding an area of interest, such as creating zones based on specified distances. For example, used to define flood zones or define zones of inclusion or exclusion. So as I said, if you, let's say you create a buffer to define the flood zone around a river or around a valley, within a valley, it would be considered an exclusion zone. Because if you have any, let's say you are a planner and you want to manage development, you would want to ensure that no one goes inside that boundary that you've just created your buffer for in order to carry out any activities. So that would be an exclusion zone. An inclusion zone, for example, might be if you generate a certain buffer distance around a, let's say around a school, and you define a distance and say all residents that fall within that buffer distance can attend this school. Okay? Oh, here is the map algebra example. So if you recall, we said this type of analysis is performed on raster dataset. It enables users to specify mathematical relationships between the features. Map values may be added, subtracted, multiplied, and divided, and the resulting layer can be stored for future analysis. So if you recall, we have the two layers: this fire hazard layer, flood hazard layer. Each value is a reflection of the level of the hazard. In this example, we add them together in order to produce a result that is called a hazard risk map. So this hazard risk map actually represents the level of hazard of both fire and flood. Right? So when we add the numbers together, we will get an output. Where you have values for only one layer and none for the other, we do not actually have a value in the final result in those cells. Okay, so now we're trying to put everything in context here. What are the 4 stages of spatial data management? So remember, this is what a GIS is. It's a geographic information system. And throughout the semester, we have been talking about all of these different stages. So now at this point, we have been focusing mainly on spatial analysis. So now we want to put the spatial analysis topic into the broader context for the course content. So if you recall, when we started this semester, we started talking about data input. We talked about things like data models. We learned about raster and vector. We learned about how we can collect data, how we can input data into your GIS, right, such as scanning, digitizing, etc. The next stage, once the data has been put into the system, the data now has to be stored. So remember, it has to be stored in a particular way. If it is a raster data set, it's stored in an array of cells. If it's a vector, it has to be stored as the map and the attribute table, etc. So the storage has to be planned and organized. Data has to be retrieved, and the data has to be managed. So what do we mean by all of this? Some of the tasks that you would carry out at this stage would be your correction of data, your updating of data if it's old data that needs updating, and you find you would also need to carry out some reclassification at this stage. The next stage is your data analysis. This is the stage that we have been talking about so far today. This is where we manipulate the data. So remember, the data has already been organized and prepared for you in step 2. In step 3, we now begin to manipulate the data. For example, you carry out queries, you carry out intersections, buffering, etc. We also do some data exploration. Remember, a simple example of that would be our visual analysis, as well as confirmation of data. So all of this is part of your data analysis. And the final stage would be your output, which would be your display and map generation. Right, so that would be, for example, display on your screen, as well as your final preparation in terms of your map layout with all the essential elements, such as your north arrow, title, scale, etc. So what is the importance of the spatial perspective? Why is this so important? I mean, we have other information systems. What makes it more beneficial to have an information system that is geographic is that it provides a simple but useful framework for handling large amounts of data. So we would have addressed this early in the semester. For example, if you have a spreadsheet full of data in front of you with thousands and thousands of records, it's hard for you to assimilate that information and to understand it in that form. However, if you saw it represented on a map, immediately you would be able to discern and recognize patterns and trends in that data. The spatial perspective also permits easy access to information on the relative location of objects and events. For example, you'll be able to do quick queries to extract subsets of data. It also allows objects or events of various types to be linked and formalized in the GIS as overlays. Alright, so other data layers can be added to the GIS and even linked to some of the features. So implementing the spatial analysis, how do we put it to work? How do we make it happen? Alright, so complex analytical functionality is not a part of the typical standard commercial GIS software package. For example, what do we mean? The one that we use in the lab is pretty standard. So you have a fair amount of functionality there, but when you want to do really complex spatial analysis, it would be necessary to have add-on packages or extensions. Alright, and these would not be available in the standard package that we use unless you upgrade the license level. So for example, spatial analysis extensions such as the spatial analyst extension in ArcGIS would be available only at a higher license level. Okay, also you have specialized statistical packages available. So the point of this slide really is to tell you, if you want to actually carry out spatial analysis in a GIS software environment, there are very specific tools that you will have to use to make it happen. Right, you have the basics that are available, such as select by attribute or select by location, and then you have specialized tools available that require an upgrade in license level. Okay, and lastly, we have a short list, and by no means the extent of the examples of how, various circumstances in which spatial analysis can be carried out. For example, you use spatial analysis to look at the distribution of diseases, traffic management and land use planning, environmental problems, for example, oil spills or chemical spills, solid waste pollution, etc. What do we have here? Landscape characterization and measurement, social, cultural, and economic analysis, and the list can go on and on. So I'm not really going to bind you to this specific list, but these are some examples of where we can carry out spatial analysis using GIS tools. Okay, so I want to thank you for joining me today for today's lesson. Please refer to eClassroom for further instructions.